Hello again. By now, hopefully you've watched all the videos related to the normal distribution. And now we're going to use the normal distribution to look at something a little more complicated. We're going to be looking at the distribution of a sample mean. And in order to understand this, I want you to think about the idea that if I have a random variable x, it can follow some sort of random distribution. And I could think about adding up a whole bunch of random variables. And if each of these random variables follows some sort of distribution, then the sum of those random variables is also a random variable. I can divide by a constant, and this whole thing is still a random variable. So it's possible to think of the sample mean as its own random variable. And that's what we're going to be doing in this section. So first we need to talk about what the sampling distribution is, and that's the probability distribution of some sort of sample statistic, such as x bar. And we form this thing when we take samples of size n from a population. Now I want you to think about the idea that we could go out, say, into the SRU community, and we could say we're going to take a sample of 100 students and ask them a question. Maybe, are you happy that we're online taking classes? And we're going to get some proportion that are going to say yes and some proportion that are going to say no. So we're going to get an estimate for the proportion that say yes. That estimate is an estimate of what the total population might say if we could talk to everybody. Okay, so you get the idea? We're actually going to go out and we're going to grab a sample of 100 students. Now I want you to think about us doing that over and over and over again. Throw our 100 students back into the pot and go out and take a new sample of 100 students. Now the second time we take a new sample of 100 students, we're probably going to get slightly different estimates because we have a slightly different sample. So if we do this over and over and over again, we're going to get a whole bunch of different estimates for that true proportion of the population that's happy that we're doing our classes online. This idea that you could sample over and over and over again and form this kind of distribution of values that you could get, that's what's behind the work that we're going to do in this section. So you could think about doing this with the sample mean. We could go out, grab 100 students, measure something, take the average, say GPA for the 100 students, throw them all back and do this over and over and over again. So we could think of having a sample mean number 1, and then for a new sample, a sample mean number 2, and then for a new sample, a sample mean number 3, and so on. And if you were to be able to take all of these potential samples and look at all their values together, that would give you the sampling distribution of that sample mean. All right, this is just a visual. We're on slide 3. Give you an idea of what this might look like. You're grabbing different samples. Notice that the samples could overlap with each other. That's perfectly plausible. But that there's some total number of possible samples that you could take. So once we've done that, the question might arise as to what's the sampling distribution look like? What does the distribution of the sampling mean look like? Well, one thing we know is that if the average for the underlying population is mu, so if for x, the average is mu, then for x bar, the average is also mu. And that kind of makes sense, right? You would hope that if you could take every possible sample out there and get all the possible sample means you could get, that the average of those sample means would also be the average for the whole population. Where things change is with the standard deviation. So while the mean is going to be exactly the same as it would be for a single unit in the population, the standard deviation is going to be lower. So if for x we have sigma as our standard deviation, for x bar, we're going to have sigma divided by the square root of n. This thing, this sigma divided by the square root of n, has a special name, and that name is the standard error of the mean. All right, so what have we figured out so far? We've talked about the idea that a sample mean could have its own sampling distribution, because every time you took a new sample of the population, you would get a slightly different value for that sample mean. So suppose that a variable x of a population has a mean mu. Notice we're not even talking about what the probability distribution is for this thing. We just are saying we have this random variable x, and it has a mean of mu and a standard deviation of sigma. Then if we're going to take a sample of size n, we know a few things. First of all, we know that the mean of the x bars is equal to the mean for the population. We also know that the standard deviation for the x bar is going to be the standard deviation for the population divided by the square root of n. If x is normally distributed, this is kind of cool. then so is x bar. So basically, if I have a bunch of random variables that are all normally distributed, then the sum of those random variables is normally distributed. And I can multiply that whole thing by a constant, and that whole thing is still normally distributed. Therefore, x bar is normally distributed anytime we know that underlying x random variable is normally distributed. Here's the fun part. As the sample size gets very, very large, it turns out that x bar is approximately normally distributed regardless of the distribution of x. Now this is some pretty funky, cool math magic. We're saying we don't know what the distribution of x is. We know that it's distributed with some mean mu and some standard deviation sigma, and as long as n is large enough, that's going to imply that x bar is distributed normally with that same mean mu and with the standard deviation sigma over the square root of n. How cool is that? This is actually the most powerful result in the field of statistics. All right, so let's talk about what does that look like practically. So here's an example of an underlying variable x's distribution. So we have one that's kind of normal looking, one that looks kind of like a J shape, and one that looks pretty uniform. If we go up to a sample mean with size n equals 2, the distribution of that sample mean, so remember that would be x sub 1 plus x sub 2 over 2. The distribution of that sample mean, it looks a lot like the original distributions. Except for this one. That one's kind of funky, right? It looks like a triangle. But as n gets bigger and bigger and bigger, all of those distributions start looking closer and closer and closer to each other, regardless of the original distribution for the random variable. All of these sampling distributions for x bar look pretty similar, don't they? By the time you get to n equals 30. Pretty cool result. All right, so just to drive this point home, we're going to do a simulation. And the simulation we're going to do is we're going to take a box and we're going to put 4 slips of paper into that box. The slips of paper are going to say 1, 3, 5, and 7 on them. And we're going to randomly select 2 pieces of paper from that box with replacement. So we could select 7 twice, we could select 5 twice, we could select 1 and 3 or 3 and 5. So there's going to be a total of 16 possible samples we could get. And what we want to do first is find the mean and the variance and the standard deviation of the population itself. And then we're going to look at that sample mean, that is x sub 1 plus x sub 2 over 2, because we're pulling 2 slips of paper. So we're going to take that x bar, where n equals 2, and we're going to look at the distribution of that. All right, so let's start with part A. Well, if you sum this up, 1 plus 3 plus 5 plus 7, you get 16. 16 divided by 4 is just 4. And we already know how to use software like Excel to find the variance. So we would just plug in these 4 values into Excel, look for the variance, and we would get that it's 5. And the standard deviation would be the square root of 5, or 2.236. So those are our underlying parameters in this particular population. All right, so now that we've done that, let's graph the histogram for the population values and see what it looks like. And there it is, because everything has equal probability of being selected, right? So we have a 25% chance of getting 1, a 25% chance of getting 3, 5, or of 7. It's a uniform distribution. It's called a discrete uniform distribution. So now let's look at all the possible samples of size n equals 2, and then calculate the mean for each of those samples. This is going to be fun. Not really, but we're going to do it anyway. So here are all our possible samples. I told you there were 16 altogether. Here they are listed. So clearly x bar for this one, 1 plus 1 is 2 divided by 2. That one's going to be 1. This one is going to be 3, because 5 plus 1 is 6, divided by 2 is 3, and so on. And we can go through and calculate all of those, and we get all these potential different sample means. These are the means that form the sampling distribution of the sample means for this toy problem, where we have a population of size 4. All right, well, let's look at the probability distribution of those sample means. Keep in mind that here we only had 1 occur once, but some of the other values like 2 occurs 1, 2 times, 3 occurs 1, 2, 3 times, 4 occurs 1, 2, 3, 4 times. I know you see a pattern, but 5 only occurs 3 times, 6 only occurs 2 times, and then 7 occurs 1 time. So we end up with a probability distribution that looks like this. And we can actually create a histogram of that, and we're going to see that histogram would look pretty darn symmetric. It's going to start looking like the normal distribution. All right, we want the mean, the variance, and the standard deviation of the sampling distribution of the sample means. So let's take a look. Well, we know that our mean is going to equal the mean of the underlying population, so that's just 4. Okay, if sigma over the square root of n is the standard error of the sample mean, then sigma squared over n would be the variance of the sample mean, right? Because we're just going to square this thing to get that variance of the sample mean. So that's what we've got here. Sigma squared is 5. We learned that when we figured out that value for the population. And then we're going to divide by n, which is 2. So the variance for the sample mean is 2.5. And then we could take the square root of that to get about 1.581. We have another option, though. If you recall, sigma was about 2.236. So we also could have taken that 2.236 divided by the square root of 2, and we should have ended up with the same result because that's sigma divided by the square root of n. And actually, if we now look at the results here, we're going to see that that's exactly what we can do. Here's sigma divided by the square root of n. That's square root of 5 divided by square root of 2, 2.236 divided by square root of 2, and so on. Finally, we can graph the probability histogram for the sampling distribution of the sample means, and look at that. It's looking awfully symmetric, awfully bell-shaped. It approximates a normal distribution. So this was a little toy example just to give you the idea that you can treat the sample mean as its own random variable, and when you do that, no matter what the original distribution is, even if it were uniform and flat like our original distribution, remember the original distribution was for 1, 3, 5, and 7, that each one had 25% probability of being selected. So that was a discrete uniform distribution for the original population. Even in that case, even with as small a sample size as n equals 2, we end up with a symmetric bell-curved shaped distribution for the sample mean. All right, so going back to the idea of the sampling distribution of the sample mean for a normally distributed variable, remember we talked about the fact that if x is distributed normally with mean mu and standard deviation sigma, that automatically implies that x bar is also distributed normally with mean mu and this time standard deviation sigma divided by the square root of n. That is automatic. That is true. That is provable. So here's an example we can look at because it is a designed example. IQ is actually designed to be exactly normally distributed. And in fact, the scores are standardized so that the mean is 100 and the standard deviation is 15. So what happens if we start looking at an x bar for IQ where n equals 4? Well, first of all, we'd expect our mu of x bar to also equal 100, but now our standard deviation for x bar is going to equal 15 divided by the square root of 4, which is 15 divided by 2, or 7.5. So here's a simulated example, and if you look, yeah, we got about 7.5 above and below the mean is our inflection point, indicating that that is indeed about where the first standard deviation falls. So just happens to work pretty perfectly. Here's another set of examples with different sized sample sizes. So this was the normal curve. They're saying that the standard deviation is 16. I had always heard 15 before. But here we have n equals 4, and because n equals 4, we take that 16 and divide by the square root of 4, and we get 8. And then if n equals 16, we take that 16 and divide the square root of 16, and we get 4. 16 divided by 4 is 4. And you can see what happens to the curve. It keeps getting skinnier and skinnier and skinnier as that standard deviation for the sample mean gets smaller and smaller. All right, we're going to stop there and we're going to start with the central limit theorem in the next video. See you then.